A ball rolls off a table and falls 0.75 meters to the floor, landing with a speed of 4.0 meters per second. A. What is the acceleration of the ball just before it strikes the ground? Okay, so I got a little diagram of a table here. So we're gonna have a before picture. So there's a ball rolling this way, and after some time passes, what's gonna happen to the ball is what we all think. It's gonna, it was rolling that way, and it fell off the table, and it struck the floor, and they tell us that it hit the floor with a speed of 4 meters per second. So we're coming at it this way to the floor at 4 meters per second. Okay. I encourage you to just pause the video for a moment and work out the problem by yourself. Okay, so I assume you've paused it, and now that we've kind of discovered what's going on in the picture, it makes it, I hope, a little bit more clear on how we're going to go about solving the problem. The first part is very simple, straightforward, so don't get, thrown off by these freebies. What is the acceleration of the ball before it strikes the ground? Okay, well, we know that when we use kinematics, and we know this is a kinematic problem because we have a distance and a speed and an acceleration, so clearly we're going to use kinematics. We're going to assume that the acceleration is going to be constant, but in what direction? So we're rolling this way. Once we start rolling the ball, unless the ball has like some kind of internal engine, which most balls don't, not that I'm familiar with anyway, it's going to have no acceleration. It's just going to go. The falling part, on the other hand, it does have acceleration. We know that we live on the surface of the Earth, and on the surface of the Earth we have a certain acceleration, and that's just the acceleration of gravity. Okay, so if this ball is falling, if this ball were up here, we would have a speed this way, and an ever-increasing speed in this direction. So our only acceleration in play is the acceleration due to gravity, and we all know that that is 9.81 meters per second squared. Okay, part B. What was the initial speed of the ball? What was the initial speed of the ball? Okay, so let's talk about our kinematic equations. All of our kinematic equations are based on how long it takes something to move through a certain amount of space, or how long it takes for something to go a certain speed through that space. So we're kind of just using time and displacement and velocity, and by virtue of these three, we can get acceleration, or from either of these three, we can get the others. We kind of have to make a decision on which formulas we can use. Now, there is a formula that uses acceleration, right? So that's great. We have a displacement. We know that the table was so high, and we have an acceleration, and, oh, wait, we have this acceleration. We don't have an initial speed, and we also don't know how long it took. We could go through and find out how long it took by plugging in this in one direction, maybe getting, well, we still don't have an initial speed, so that's not going to work. Okay, we also have one. So let's check what we have. We have final velocity. Okay, good. We have a final velocity in this kind of diagonal direction. We don't have an initial velocity. We do have an acceleration in the downward direction, and we do have a displacement in the downward direction. Okay, so far we have a formula we might be able to use as long as we understand really what's going on. Now, in these kinematic problems, almost invariably, unless it's like a very simple, maybe like one-off problem, we're going to be using triangles. So we have the final speed of the ball, and that to us is going to be this diagonal line right here. And they told us that was 4.0 meters per second. Great. Okay, so this is our resultant vector. We need to have two vectors that add up to it. So we could have one going down. We know that there's a speed in the vertical direction, and there's also got to be a speed in the horizontal direction. Now notice that I put the tail of the horizontal direction right on the tip of the vertical direction. We could have gone the other way. We could have made our triangle look a little different, but this way is more consistent with our picture. So just always make sure that you have your vector addition lining up with your picture. So we have 4.0 meters per second, and if you'll notice, this is the hypotenuse of the triangle. So we know there's going to be a right angle here. We do not know what this angle is here. So mystery angle at the top. But we do know that this is a right triangle at the very least. Okay, great. So how can we figure out this side of the triangle? Well, if only we knew two sides of the triangle, we would know the third side because we have, if we label these sides A, B, and C, we know that A squared plus B squared equals C squared, right? Like from elementary school. That's kind of the first fancy really equation that we learned using, multiple letters. It's a lot of fun to just kind of say. So we know that we could find B squared if only we knew what C and A were. Well, good news. Like we said, these vectors work independently of each other. We don't have to worry about the horizontal movement of the ball if we don't want to right away. Let's treat it as a one-dimensional problem, vertically first. So we can use our formula right here, which we've written. So we can use this formula, and we want to know what A is. So A is going to be our final velocity in the vertical direction. Now, if we look at this equation here, A is v final in this equation because we're only talking about up and down. So we don't need to know what's happening horizontally, just vertically. Vertically, zero velocity up here. So right at that point, it still has zero velocity. So v initial, that's zero. V final is what we want. Great. Now the acceleration, we know that. We answered in part A. It's 9.81 meters per second squared. 9.81 meters per second squared. Okay. Displacement, we know that too. In the problem they tell us that it's 0.75 meters high. This table right here is 0.75 meters. Great. Okay, so for the displacement, we just say 0.75 meters. Okay, I think we're in business. Let's make sure everything's going to cancel out as we do our work. Okay, so I'm going to switch writing utensils here so it's just a little better, and my pen's not cooperating so well. We know that V final is going to be equal to the square root of 0 squared, which is nothing, to acceleration of gravity, right? So I'm going to leave it as g. Okay. Meters times meters is meters squared. Meters squared over second squared. Square rooted, we square root them both. We end up with meters per second. Everything works out. Story checks out. Great. Okay. So we can go ahead and solve. So 2 times 9.81 is 19.62 times 7.5. Sorry, 0.75 is 3.83. Okay, great. So we can take that V final, and this is going to be the same as A. So A is equal to 3.8. So this right here, this A, is 3.8 meters per second. Great. Okay. We know A, we know C, we can finally find what B is. So this is going to be C squared minus A squared is equal to B squared. Great. And if we want to get rid of that squared on that side, we'll just square root this side and just plug your numbers in. Okay, so we found the bottom side of our triangle. We found the horizontal speed of the ball. And you might be saying, okay, well, hang on, that's the horizontal speed of the ball down here. I want to know what it is up here. Well, you're in luck because there's nothing pushing back on the ball here if we ignore air resistance, which we are in this problem. So this speed has to be the same as the speed it started out with. So the initial speed of the ball is 1.2 meters per second. 1.2 meters per second. Great. Okay, for part C of the problem, we want to know how fast we need to start the ball rolling for it to end up going 5 meters per second on the floor. Well, we already have our Pythagorean formula over here, so just plug in the numbers that we need. We know that the vertical acceleration is not going to change. The only thing that can change is the bottom part of our triangle. When you plug in our numbers, we'll have the initial speed that we get the ball rolling on the table. So keep working on those physics problems, and good luck.
That was awesome.